Hi, and welcome to Netbooks Video Learning. I'm Guy. And today's episode is Differential Calculus Part 2. Before we start, let's have a look at the goals for the video, based on the Annual Teaching Plan 2. The Annual Teaching Plan requires learners to comply with the learning outcomes for every topic. These learning outcomes will be tested in your exams. Let's have a look at the learning outcomes for this topic. You are required to be able to factorize third-degree polynomials by applying the factor and remainder theorem. We will cover this in today's video through theory and examples. You are also required to be able to sketch cubic graphs by following a set of steps. We will cover this in today's video through examples. You are also required to know what a second derivative is, and how we can apply it in finding the nature of the turning points of cubic functions. We will cover this in today's video through examples. You are required to find the equation of the tangents to functions. We will cover this in today's video. Firstly, let's look at the remainder and factor theorem. To explain our remainder and factor theorems, let's look at an example we're already familiar with. A simple fraction, 20 over 6. In this fraction we can label our elements that represent the division as follows: 20 is the dividend, 6 is the divisor, 3 is the quotient and 2 is the remainder. We can apply the same principle when dividing algebraic polynomials. Suppose we have a polynomial f of x. We can divide this by a factor x plus b and represent it in the same way as our simple fraction. Here we have f of x as the dividend, represented by 20 in our simple fraction. We have a x plus b as the divisor, represented by the 6 in our simple fraction. Q of x and r represent out quotient and remainder, represented by 3 and 2 respectively in our simple fraction. Now that we understand the format of our polynomial division, let's define our remainder and factor theorems. The remainder theorem is a rearrangement of the polynomial fraction discussed earlier. The dividend is equal to the factor times the quotient, plus the remainder. Or f of x is equal to ax plus b times q of x, plus r. The factor theorem builds off the remainder theorem. We say that if the dividend is evaluated at negative b over a and returns a value of 0, we know that ax plus b is a factor of the dividend or polynomial. In other words, we know that dividing f of x by ax plus b will not yield a remainder. Let's attempt an example together. As always, we recommend that you do this in your book with us. Given the functions f of x, g of x and h of x, answer the following questions listed below. Determine the remainder if the function f, 5x cubed plus 5x squared, plus 3x, plus 2, is divided by x plus 2. We will use long division to solve this problem. We focus on the first term in the dividend, which in this case is 5x cubed, and divide that by x in the divisor. The result, 5x squared, is then multiplied by the divisor, x plus 2, this gives us 5x cubed plus 10x squared. We subtract this result from the dividend, bringing down the next term as well. This gives us negative 5x squared plus 3x. We repeat the same process, focusing only on the first term, which is negative 5x squared. We divide this by x in the divisor and get a result of negative 5x. We now multiply it with the whole divisor again. This means we now subtract negative 5x squared minus 10x from the remaining portion of our dividend. We get a result of 13x plus 2 by bringing down the next term from the dividend. We continue this approach until we find our remainder, a value of negative 24. Since we ended up with a remainder, we can say that x plus 2 is not a factor of f of x. Let us attempt the second part of the question. Determine the value of k, if x plus 2 is a factor of g. If so, then divide the function g by x plus 2. Since we know that x plus 2 is a factor of g, we can find the x value where g equals 0, using the factor theorem. We let the factor x plus 2 equals 0, we solve for x and get a value of negative 2. This is the x value where g equals 0, according to the factor theorem. Knowing our function of g, we can substitute a y value of 0 where we have an x value of negative 2. We are now left with only one unknown in our equation, which is k. We can easily solve for k and get a value of 7 over 2. By substituting in our value of k, we can get the complete equation for g of x. We now need to divide g of x by x plus 2. We will use synthetic division for this. Let's recall our equation for g of x, solved in the previous part of the question. To use synthetic division, we list the coefficients of all our terms in the equation for g of x. We then need to identify our dividing factor. We do this by letting our divisor, x plus 2, equal 0. We solve for a factor of -2. The first step in synthetic division is to bring down the first coefficient, in this case 3. Next, we multiply our dividing factor with the value brought down, we get a value of -6. We now add the next coefficient, 7/2, to the calculated value of -6. We get -5/2. We repeat the process, we multiply our dividing factor with the value brought down, we get a value of 5. We now add the next coefficient to the calculated value of 5. We get 3. Once more, we multiply our dividing factor with the value brought down, we get a value -6. We now add the final coefficient to the calculated value of -6. We get 0. The values we have calculated each represent coefficients of our quotient. Remember, the highest power of the quotient will be 1 power lower than the highest power in our dividend. In this case, the highest power of our dividend was x cubed, so our quotient will start with x squared. The last position represents our remainder. In this case, we have no remainder, since x plus 2 was a factor of g of x. We can now write out our quotient in full. So we can say that g of x, divided by x plus 2, is equal to 3x squared, minus 5/2x, plus 3. We have now covered learning outcome 1 in this video. Let's move on to the next part of the question. We are asked to sketch the graph of h of x. In order to sketch a cubic graph, we need to consider the turning points, concavity of the turning points, x-intercepts and y-intercept. Let's start by finding the turning points. At the turning points of any cubic function, the gradient is equal to 0. So we need to solve the gradient. In order to solve our gradient, we will find the derivative of h of x. We will use the rules of differentiation. We do not need to solve the derivative from first principles unless specifically asked. If you are unsure of how to apply the rules of differentiation, please ensure you have watched our previous video, Differential Calculus, Part 1. We solve our derivative as 3x squared, plus 6x, minus 9. The turning points have a gradient of 0, so we set our derivative equal to 0 and solve for the x values of our turning points. We can factorize this trinomial to solve our x values as x equals -3 and x equals 1. Those values represent the x values of the turning points of h of x. We can solve the y values by substituting the x values back into the original function for h. Be sure to use the original function, not the derivative here. Remember that we want turning points to sketch our original function h of x. We substitute x equals 1 into h of x and solve for y. We get the point 1, -5. We repeat this process for x equals -3, and get the point -3, 27. We can now plot these turning points on our Cartesian plane. Now we need to figure out the concavity of the turning points. What is concavity? It is simply the shape of the graph, either a smiley face or a sad face. We use the second derivative to evaluate the concavity. An easy way to remember the evaluation is, if the second derivative is positive, it's happy and smiling, which is concave up. If the second derivative is negative, it's sad and pouting, which is concave down. The second derivative is found by simply taking the derivative of the first derivative. Once again, we can just use our rules of differentiation. We find our second derivative as 6x plus 6. When we evaluate the second derivative at our first turning point, x equals 1, we get a value of positive 12. This means concave up. When we evaluate the second derivative at the other turning point, -3, we get a value of -12. This means concave down. We can now draw in our concavities on the graph. Finally, let's find our intercepts. To find our y-intercept, we let x equal 0 in the function h of x. We get a y value of 0, and the point 0, 0. To find our x-intercepts, we let y equal 0. We can factorize this equation in order to solve for x. We can apply the quadratic formula in order to find the x values for the trinomial. We get 3 x-intercepts for this cubic graph. Now let's add our intercepts to the graph. Finally, we can complete the sketch of our graph. We have completed the second and third learning outcomes for this video. Now let's move on to the final part of the question. We now need to determine the gradient of the tangent to the graph, at x equals -2. Looking at the graph, we are expecting a tangent with a negative gradient. We need two things from this graph: the coordinates of the point on the tangent line, and the gradient of the tangent line. Firstly, in order to find the point on the tangent line, we recognize that it is, of course, a point on h of x as well. We have the x value of the point as -2. So to calculate the y value, we just substitute the x value into h of x. We get the y value as 22, and the point is -2, 22. To find the gradient of the tangent, we just need to evaluate the derivative, at x equals -2. We get a gradient of -9. Remember, we expected this negative gradient. Now we can solve the equation of the tangent line, using the standard form of a straight line. We substitute our gradient and known point into the equation. We get the equation of the tangent as y equals -9x, plus 4. The key points for this problem are, when finding the equation of a tangent to a cubic function, we find the coordinates of the shared point using the original function, evaluated at the given x value. We can find the gradient of the tangent using the derivative of the original function. We have now addressed all the learning outcomes of this video. Join us for applications of differentiation in our next video, Differential Calculus Part 3. As always, it has been a pleasure. See you again on NetBooks Video Learning.